Hello, Dr. Stevens here with the LEGO Problem Revisited, Alternative Representations, and Auxiliary Variables. We're going to be talking about some things we haven't discussed too much in class, and in particular, the relatively important idea of an auxiliary variable. An auxiliary variable is a variable that you don't really need, but you might want to use anyway. And we'll do this in the context of the LEGO problem that we did in class on the first day. You'll remember that. There were 8 different pieces of furniture that you could make out of the blocks that you had. I supplied you with 20 of the small blocks, 20 of the medium-sized blocks, and 20 of the large blocks. And you were supposed to build furniture that was worth as much money as possible. There were some extra rules. For example, every table had to have at least 4 seats around it that you could sit on. A seat is either a chair or a bench. And you couldn't have a coffee table unless you had a couch, nor could you have an end table. Every couch let you have 2 end tables and up to 1 coffee table. With that in mind, you tried to find the best answer. But now let's do it from a linear programming perspective. First of all, of course, we're going to need decision variables. Well, our decisions in this problem are how many of each object we make, so we have 8 decision variables, 1 for each product. Our objective is going to be to maximize profit, and we're going to have some limited resource constraints that say that we can't use any more of the small, or medium, or large blocks than the number that we have available. Then we also have some minimum performance constraints that say that we have to have at least 4 seats per table, and that we have to have, for example, also you can't have too many coffee tables, and you can't have too many end tables. The mathematics behind this is not going to be too tough. We can stick it in. Every time we make a chair, we make $10 profit. Every time we make a bench, we make $20 profit, and so on. And we have the constraints that say we can't use more than 20 small, or medium, or large blocks. And then the constraints that are imposing the conditions that we have enough chairs and so on. Let me take a look at that one in particular, the chairs constraint. You can think of it this way, that the number of seats that are made have to be greater than or equal to the number of seats that are required. How many seats do you make? Well, take the number of benches plus the number of chairs, and that's the number of seats. Number of seats required. Every time you get a table, it takes 4 more seats. So when table goes up by 1, seats required goes up by 4. And that is a perfectly adequate way of representing the requirement that you have to have at least 4 seats for every table. But maybe your head didn't go in that direction. Maybe you weren't thinking about seats. Maybe you were thinking about tables. And you wanted to say something like this. The number of tables that you make have to be less than or equal to the number of tables that you're allowed. Well, TA is how many tables you make. That's the definition of it. But how many tables are you allowed? Well, that depends on how many chairs and benches you have. 4 chairs lets you have another table. So would 2 chairs and 2 benches. But the question we're going to have to ask here is, if the variable ch goes up by 1, by how much do I increase the number of tables allowed? Well, 4 chairs would give us 1 more table, which kind of suggests that 1 chair is worth a quarter table. And by the same logic, so's a bench. No chairs or no benches would mean no tables allowed, and that would be the constant term. Now, in order to get this answer, you have to be comfortable with something called the assumption of divisibility. It's something that you always assume when you're doing a linear program, and basically it says that fractional values of variables are always okay, like a quarter of a table. So we can say that 1/4 of a table would take 1/4 of the resources of a table and would sell for 1/4 of the money. In real life, of course, that's not going to be the case. So if you don't want this sort of thing, you're going to need to do integer programming. We'll talk about that in Chapter 6. But for now, let's just deal with this and realize that while we thought about it differently, really we didn't say anything differently at all. If you take this second constraint and multiply it through by 4, it turns into this. And that bottom constraint is actually exactly the same thing as the constraint that we started with, simply written backwards. The first one was written as a greater than or equal to, the last one is a less than or equal to. But mathematically, they're identical. Okay, I want to talk to you now about what real companies have to worry about, materials and assembly costs. So let's say that we have to buy our blocks. The prices are at the bottom of the screen. And let's also say you have to assemble them. Every time I stick a new block onto the thing that I'm building, it's going to cost me $10. And I only have an $1,800 budget. How will this change my linear program? Well, the first thing is I'm going to have to know what my selling prices are. And I've told you them here. I can figure out parts and assembly cost and work out what the profit is for everything, and it turns out these profits are exactly the same as the ones that we used on the first day of class. But things are different because now I have to buy blocks and use them. So I'm going to need to make some new variables. How many small blocks and medium blocks and large blocks do I buy? And I'm also going to have a new constraint. I can't spend more money than the amount of money that I've got, which I just told you is $1,800. Let's look at the formulation. What's going to change? Well, the right-hand side of those first three constraints have got to go. We no longer have 20 blocks available. Instead, we have how many blocks we buy of each size. So, small blocks, medium blocks, and large blocks bought go on the right-hand side of the constraint. The objective itself is profit, but now it's going to be easier to think about that as money coming in minus money going out. That is, as revenue minus cost. We'll evaluate each of these separately. We'll get revenue from selling stuff. We'll spend cost by assembling stuff or buying raw materials. And of course, that brings us up to the other constraint, the budget constraint. We can't spend too much money on blocks and assembly, no more than the $1,800 that we have. So the objective and this first constraint are what we have to worry about. Let's focus for the moment on the constraint. We're talking about cost on the left-hand side. And a couple of things I'd like you to notice about it. First of all, the expression for cost is going to be kind of messy. Every time that we make something, every time that we buy something, we're going to generate a cost, which means that all 11 variables in our problem are going to appear in that cost expression. Even more, we're going to have to do it twice, because the cost will also be a part of the objective, as well as the left-hand side of the constraint. The fact that it's long and complicated and appears multiple times suggests that maybe we want to use an auxiliary variable. An auxiliary variable is a variable that you don't really need, but you might want it anyway. Why don't you need it? Well, that's because its value is completely determined by the values of the other variables. Face it, in this problem, if I know what I make and what I buy, then I know everything, and that means I know my cost. On the other hand, you might still want the variable because it shows up repeatedly in the problem, and because the expression that gives it is long and complicated. That's certainly the case in our problem. The expression for cost appears in the objective and the left-hand side of the constraint, and it's going to be a mess because it's going to depend on all 11 variables. Now, the rule is you can make up an auxiliary variable for any quantity that you want, but, and this is a big but, you must include an equality, an equals constraint in your program saying how that variable depends on the other variables in the problem. So for us, we're going to have to define cost to be the number of dollars of cost, assembly and parts, and then we can use that variable, for example, to write the budget constraint in this very simple way. Cost less than or equal to $1,800. And that's pretty much it. Almost. But you have to remember, anytime you define an auxiliary variable, and a variable you don't really need, you have to write an equation constraint that tells you how to compute it from the other variables. Here, our expression comes by looking at the costs of various activities. The assembly cost of each item is listed, and the cost of buying all of the individual blocks is as well. Add them all together, and that's the total cost. Now, it's messy to write that, but once you've got that expression, you can now use cost anywhere in the program you want. So I can now write this constraint for cost, and then write my budget constraint simply cost less than or equal to $1,800. All that's left is my objective, which is revenue minus cost. Well, cost is just the cost variable I just defined. How about revenue? The money coming in depends on the selling price of the items that I sell. So I can get it pretty simply by using the table down below to get that. Add up all the revenue coming in, subtract off our auxiliary variable cost, and that gives us the total objective function. If we put all this together, we end up with this for the formulation. And if you find its optimal solution, you'll find out that what you should do is to buy the materials necessary to construct 7 fire pits, make them and sell them, and that's it. A very different answer than we got from the in-class exercise. Alright, while we definitely could use auxiliary variables here, it's worth mentioning that, as always, we don't have to use them. I could have gotten rid of that first constraint that defined cost, and used its right-hand side to fill in the left-hand side of the budget constraint right below it. All that junk less than or equal to $1,800. In the same way, I could have replaced the word cost in the objective with that entire long expression that you currently see on the right-hand side of the cost equals constraint. It would have had a lot more terms, but the mathematics would have been entirely equivalent. So we did save some writing here by using the auxiliary, but sometimes we gain a lot more than that. You never have to use an auxiliary, but they can be useful in a number of kinds of problems. For example, networking problems. Suppose I have a location where people are entering and leaving, but no one's actually simply staying there. Then if I know how many people enter through each one of the indoors, and how many people leave through each of the outdoors except for one, Well, then I could figure out how many people left through that last store too, by simply adding and subtracting the appropriate numbers. So it's not an independent quantity, and there's an equation that ties all those variables together that would appear inside the linear program. A lot of times you'll see more than one auxiliary variable. You'll see families of them. A common example of that is inventory problems. Imagine you start with a certain amount of stuff. Then each month you make some and you sell some. So at the end of each month you have inventory. Those inventory quantities are entirely determinable as long as you know how much you started with at the beginning, how much you made each month, and how much you sold each month. So they're really not necessary variables, but they're very important quantities. So in almost every formulation of a linear program involving inventory, we're going to have a family of equality constraints that define those inventory variables. A similar thing happens when we're talking about cash flow. If you start out with a certain amount of money, then have a bunch of deposits and a bunch of withdrawals, well, then at the end of each month, for example, you could figure out what your remaining balance would be. The remaining balance is an auxiliary variable. It depends only on how much you started with, how much you deposit, and how much you withdraw. But it's a very important quantity which tends to come up a lot. So because of that, we would probably define a variable for how much money you have on hand at the end of each month. And all of those would be auxiliaries. So all of them would require equality constraints.